Section 10.2. Comparing two population mean with independent samples and unknown population standard deviation, or sigma 1 and sigma 2 are unknown. When population standard deviation are not known, which is a common situation, we substitute the sample standard deviation in their place. This substitution affects the hypothesis test in two ways. The student t distribution is used in place of the normal distribution to identify the rejection region. Both populations need to be normally distributed unless both sizes are 30 or larger. If the populations are not normally distributed, the t distribution can still be used to identify the rejection region if both sample sizes are 30 or more. This is because the shape of the t distribution approaches the normal distribution as the sample size increases. We have two cases to consider when the population standard deviation are unknown. Case 1. The population variance are equal. Sigma 12 equal to sigma 22. Case 2. The population variances are not equal. Sigma 12 not equal to sigma 22. Conducting a hypothesis test to compare the difference between two means with independent samples and unknown population standard deviation, sigma 1 and sigma 2 are unknown, using equal population variances. Suppose that two samples were randomly selected from the same rat population. The rats in the first sample were surrounded with a very luxury a rat could imagine. The second rat samples did not have it quite so good. After the rats spent 3 months in this environment, the size of their brain were measured by weight to gauge its development. Table 10.4 summarizes the finding. Population average brain weight in gram sample standard deviation sample size X bar. Lucky rat is 2.60. Less fortunate rat is 2.10. Because the sample size are less than 30, we need to assume that the brain weight in these two populations both follow the normal probability distribution. Suppose the researcher would like to establish the more stimulation would lead to larger brain weight using alpha equal to 5%. For this hypothesis test, we need to assume that the two samples are independent of each other. In other words, the brain weights of the lucky rats have no effect on the brain weight of the less fortunate rat. We will use the following steps to demonstrate the hypothesis testing procedure. Step 1. Identify the null and alternative hypothesis. We will start by defining each population as follows. Population 1, lucky rat. Population 2 is less fortunate rat. The hypothesis statement for this example is as follows. Null hypothesis, mu1 minus mu2 less than or equal to 0, or population 1 has brain that are less than or equal to population 2 in weight. Alternative hypothesis, mu1 minus mu2 greater than 0, or population 1 has brain that are greater than population 2 in weight, where mu1 is the sample mean brain weight of the lucky rat population. mu2 is the mean brain weight of the less fortunate rat population. This is a one-tail or upper test because the researchers are investigating whether population 1 has an average brain size larger than population 2, or as stated in the alternative hypothesis, or H1, also known as the research hypothesis. Step 2. Step a value for significant level alpha. For the rat brain research, we will use alpha equal to 5%. Step 3. Calculate the appropriate test statistic. The test statistic for a difference between population mean with sigma 1 and sigma 2 both unknown, but assumed to equal is shown in equation 10.6. T x bar equal to x bar 1 minus x bar 2 minus mu 1 minus mu 2 of null hypothesis divided by square root of sp square times I divided by n1 plus 1 divided by n2, where mu minus mu 2 of null hypothesis equal the hypothesized difference in population mean. SP2, the pool variance. The pool variance is simply the weighted average of two sample variances drawn from two populations. The pool variance can be calculated using equation 10.7. SP square equal to n1 minus 1 times s1 square plus n2 minus 1 times s2 square divided by n1 minus 1 plus n2 minus 1, where s1 square equal to the variance of the sample from population 1, s2 square the variance of the sample from population 2, n1 and n2 the sample size from population 1 and 2. Using the data from table 10.4 for our rats example, the pool variance is calculated and it is equal to 0.5163. Applying the equation 10.6, our t-test statistic is calculated and it is equal to 2.32. Step 4. Determine the appropriate critical value. The test statistic shown in equation 10.6 follows the student t distribution with n1 plus n2 minus 2 degrees of freedom. For the rats example, the degrees of freedom, or df, equal to n1 plus n2 minus 2 equal to 20 plus 25 minus 2 equal to 43. Using table 5 in Appendix A for a one-tail or upper test with 43 degrees of freedom and alpha equal to 5%, the critical t-score is t alpha equal to 1.681. Step 5. Compare the t-test statistic, or tx bar, with the critical t-score, or t alpha. This comparison is used to decide whether to reject or fail to reject the null hypothesis. Table 10.5 summarizes several possibilities tests: hypothesis, condition, and conclusion. In our rat example, which is a one-tail or upper test, tx bar equal to 2.32 and t alpha equal to 1.681. Because 2.32 is greater than 1.681, we reject the null hypothesis according to the decision rule shown in table 10.5, in which the tx bar is clearly in the shaded reject null hypothesis region. Step 6. Approximate the p-value. The limitation when using t-distribution for hypothesis testing is we can no longer determine a precise p-value as we did using the normal distribution. This is because the structure of the t-table in Appendix A relies on the sample size or degree of freedom. However, we can still approximate the p-value when using the t-distribution. Please check Table 10.6. Recall that t-test statistic or tx bar equal to 2.32. We need to find the critical t-score along the n-1 equal to 44-1 or 43 rows in Table 5 from Appendix A. Table 10.6 shows this value to be between 2.017 and 2.416. To find the corresponding p-value, we go to the one-tail row and find the p-value is between 0.025 and 0.010. Even though we do not have a precise p-value, because alpha equal to 5%, we can reject the null hypothesis. Step 7. State your conclusion. Rejecting the null hypothesis means we have support for alternative hypotheses. According to these two samples, we have evidence to conclude that the average brain size of the lucky rat population is larger than the average brain size of the less fortunate rat population. Conducting a hypothesis test comparing the difference between two means with independent sample and sigma 1 and sigma 2 unknown. Unequal population variances. There are many situations in which the population variances are not equal, or we simply cannot verify that they are equal. Under this condition, the procedure from the previous section changes slightly. Let us use the following example. A consumer group would like to investigate if there is a difference in fuel economy for the following two scenarios using alpha equal to 5%. Traveling in a particular car model with an air conditioning on the window up during the summer. Traveling in the same car model with the air conditioning off and the windows down during summer. Running air conditioner causes the engine to work harder, which will decrease the fuel economy. However, driving the car with the windows down increases drag, especially at a higher speed, which also reduces the fuel economy. Table 10.7 shows data of 10 cars with the air condition on and the windows up using 1 full tank gas on the highway and 11 cars with the air condition off and the windows down. We will use the following step to demonstrate the hypothesis testing procedure where the population variances are not equal. Step 1. Identify the null and alternative hypothesis. Let population 1 is air conditioned on and windows up, and population 2 is air conditioning off with windows down. The hypothesis statement for this example are as follows. Null hypothesis, mu1 minus mu2 equal to 0, or fuel economy of the two populations are the same. Alternative hypothesis, mu1 minus mu2 not equal to 0, or fuel economy of the two populations are different, where mu1 is the average fuel economy from population 1, mu2 is the average fuel economy from population 2. Step 2. Set a value for the significant level alpha. We will use alpha equal to 5%. Step 3. Calculate the appropriate test statistic. The test statistic for a difference between population mean with sigma 1 and sigma 2 unknown and not equal is shown in equal 10.10. T x bar equal to x bar 1 minus x bar 2 minus mu 1 minus mu 2 of null hypothesis divided by square root of sp square times I divided by n1 plus 1 divided by n2. We can use Excel to calculate the following statistic for our example. X bar is equal to 27.77, S1 equal to 1.931, N1 is equal to 10. X2 bar is equal to 26.64, S2 equal to 4.5, and N2 equal to 11. Applying these numbers to equation 10.10, our test statistic is calculated as follows. Tx bar equal to 27.47 minus 26.64 minus 0 divided by square root of 1.931 square divided by 10 plus 4.5 square divided by 11 equal to 2.83 divided by 1.488 equal to 1.90. Step 4. Determine the appropriate critical value. The test statistic shown in equation 10.10 follows the T distribution, with degrees of freedom found using equation 10.11. Degree of freedom equal to sigma 1 square divided by n1 plus sigma 2 square divided by n2 divided by sigma 1 square divided by n1 square divided by n1 minus 1 plus sigma 2 square divided by 2 square divided by n2 minus 1. We can simplify the degree of freedom calculation by calculate piece by piece, where sigma 1 square divided by n1 equal to 1.932 square divided by 10 equal to 0.3729. Sigma 2 square divided by n2 is equal to 4.5 square 11 by 11 equal to 1.8409. Now we plug values into equation 10.11. Degree of freedom equal to 0.3729 plus 1.8409 square divided by 0.3729 square divided by 10 minus 1 plus 1.8409 square divided by 11 minus 1 equal to 4.9009 divided by 0.3544 equal to 13.8 or equal to 13% or equal to 13. To obtain the most conservative hypothesis test, the degree of freedom from equation 10.11 should always be rounded down. This provides us with a larger critical t-score, which makes it more challenging to reject null hypothesis. If you round the degree of freedom calculation up, you could end up rejecting the null hypothesis when, in fact, the null hypothesis should not be rejected. This is a type 1 error, which discussed in Chapter 9. Using Table 5 in Appendix A for two-tailed tests with degree of freedom equal to 13 and alpha equal to 5%, our critical t-score is t alpha divided by 2 equal to 2.160. Step 5. Compare the t-test statistic or tx bar with t-critical t-score or t alpha divided by 2. In this example, which is a two-tailed test, we have tx bar equal to 1.90 and t alpha divided by 2 equal to 2.16. Because 1.90 is less than 2.16 on figure 10.17, the tx bar is in the do not reject region. Therefore, we fail to reject null hypothesis. Step 6. Approximate the p-value. Using Table 5 in Appendix A, go to the row with the degrees of freedom equal to 13 and find the value that bracket tx bar equal to 1.90. These values are 1.771 and 2.160. Going to the two-tailed row, we find the p-value is between 0.005 and 0.10. Because alpha equal to 0.05 is outside this range, we fail to reject the null hypothesis. Step 7. State your conclusion. Failing to reject the null hypothesis means we do not have support for the alternative hypothesis. According to these two samples, there is not enough evidence to claim a difference in fuel economy between these populations. Testing a difference other than 0. So far, in this chapter, all the examples tested whether or not there was any difference between two populations. There are situations, however, where we want to test whether the difference exceeds a certain value. For example, suppose the manager at the restaurant would like to see if the type of music played in the restaurant affects the average bill incurred per person. The theory is that slower paced music will influence patrons to stay longer and spend more compared with faster paced music. Table 10.8 shows the average bill per person during evening when the music was fast-paced versus slow-paced, along with the sample size and standard deviation. The manager would like to perform a hypothesis test to determine if the average bill per person when slow music was played exceeded by more than $3 the average bill per person when fast music was played. We will assume population variances are equal and use alpha equal to 5%. Let us define population 1 as slow music and population 2 as fast music. Our hypotheses are as follows. Null hypothesis, mu1 minus mu2 less than or equal to $3, or bill for slow music average $3 equal to or less than the fast music. Alternative hypothesis, mu1 minus mu2 greater than $3, or bill for slow music average $3 more than fast music. Use equation 10.7 to calculate the pool variance. The calculated pool variance is 29.4160. Applying the calculated pool variance to equation 10.6, t-test statistic can be calculated. The calculated t-test statistic is 2.17. Because we are assuming equal variances for this test, the degrees of freedom are as follows. Degree of freedoms equal to n1 plus n2 minus 2 equal to 23 plus 19 minus 2 equal to 40. Using table 5 in Appendix A for a 1 or upper tail test, degree of freedom 40 and alpha equal to 5%, the critical t-score is t alpha equal to 1.6.84. Because t x bar equal to 217 greater than t alpha equal to 1.684, we reject the null hypothesis. By rejecting the null hypothesis, we can conclude that the average bill when slow music is played exceeds by more than $3 the average bill when fast music is played.